So thank you for invitation. Hello, everybody. Let me introduce my joint work with my colleague Michal Turčaník and my supervisor in PhD study, Martin Papčo. We will speak about some modifications of clustering algorithms. So very shortly, doesn't work. Oops. Oh, okay. Very shortly about clustering. It's a method, or these algorithms are used to group some objects, similar objects to the groups with high internal and low external similarity. Our motivation is that common clustering algorithms use, for example, Euclidean distance or some alternatives. And the handicap of this or approach is that it may fail to reflect complex data structures. So new approach is about proposing aggregation-based dissimilarity measures in assigning objects to centroids or membership computation in fuzzy algorithms, and to replace random centroid initialization by deterministic aggregation-based strategies. Firstly, again, doesn't work. Our goals are as follows: to introduce aggregation-based modifications, define aggregational dissimilarity measure, and test a proposed approach. You will see some results in the closure of presentation. We will use this notation. We have here some data points represented as p-dimensional vectors. Centroid of the kth cluster is also p-dimensional vector. Number of clusters, number of data points. This is assignment indicator. In CRISP algorithms, it's 1 if point belongs to the cluster. And we use K for CRISP and C for fuzzy notation for number of clusters. And new symbols will be introduced when will be needed. First algorithm we will modify is K-means algorithm. Is very basic and widely used distance-based clustering algorithm. It has these steps. We randomly select K initial centroids because we need to, or we try to create K clusters. In second step, we assign points to the nearest centroid using, for example, Euclidean metric. And second step is updating of centroids. The centroids are calculated as arithmetic mean of points in clusters. This step 2 and 3 repeats until convergence. Here are some calculations for this algorithm very shortly. This is objective function, which is minimized by k-means. R and key is increased partition, can have values 0 or 1 if the point belongs to the cluster. This is calculation for assignment update. We try to find the nearest cluster. So K is the number of nearest centroid for the point. And centroids are updated by this formula. It's arithmetic mean. Very similar is fuzzy C-means algorithm. The key difference is that the clusters are fuzzy, not crisp. And we start with initialization of random membership metrics, not random centroids. But all steps are similar as k-means. The formulations or some equations are here. Objective function is very similar. We try to write them very similar to k-means, where u and k is the degree of membership, which is from a unit interval. That cluster point can be assigned to or can belong to more clusters in some time. Membership update calculation and centroid update is also, but here weighted arithmetic mean. Third basic algorithm or basic variant of this algorithm we will modify is hybrid algorithm, which combines k-means and fuzzy c-means. K-means is used to initialize centroids. So the k-means runs to convergence, and resulting centroids are used for initialization in fuzzy c-means. Here we don't need any equations because we only combine these two algorithms. In these three algorithms, we use random initialization. In K means random centroids, in fuzzy C means random membership metrics. There are some more strategies, for example, plus version, which is centroid based, so it starts always from centroids, also for fuzzy C means. First centroids is chosen randomly, and the next are chosen with probability proportional to square distance from the nearest centroid. So from the basic three algorithms, we have another three, but the difference is only in initialization. So K means plus plus, C means plus plus, and KM plus plus FCM. Advantages of this initialization is well-separated initial centroids, faster convergence, and reduced sensitivity to poor local minima. Now we get to our first modification. We use their aggregational dissimilarity measure, and here is some scheme of this aggregational dissimilarity. We calculate dissimilarities for all pairs. Then applying order reversing map, we get similarities. We use some aggregation function and get aggregational dissimilarities on vectors. And again, we apply order reversing map, not necessarily the same as the first, and get aggregational dissimilarities on vectors. This is the scheme. For definition of aggregational dissimilarity measure, we use a restricted dissimilarity function, which is defined on a unit interval, but can be widened also for more general intervals. Here are some properties of this function. It's symmetric. Maximal dissimilarity is for endpoints, null and 1, or 1 null, 0. Zero dissimilarity is for identical elements, and monotonicity is required. And we get to our aggregational dissimilarity measure, where x and y are two n-tuples. We have some restricted dissimilarity function, order reversing maps with specific properties again, but we speak about them more in a accompanying paper. and aggregation function, as I said before. So aggregational dissimilarity measure is defined as this equation. By this equation, here we have dissimilarity functions for each pairs or in each components of vectors. For example, we will compute aggregational dissimilarity for centroid and point. Then we apply order reversing map, aggregation function, and again order reversing map. Our modification, the principle is that we modify standard distance with this aggregational dissimilarity, but only in assignment or membership computation. All other steps are unchanged. We use it for these 6 algorithms, but can be used for broad class of distance or dissimilarity-based clustering algorithms. And what's changed really? This is calculation or quotient for assignment of points in classical, but we use this one. Here is aggregational dissimilarity measure. Also for fuzzy C-means, we use this calculation instead of this original. We don't need nothing else changed because all other algorithms are only combinations or some kind other strategy of initialization of centroids. Modification 2 is in the step of initialization of centroids, while in classical it's random. We try to use non-random initialization, and it's inspired by farthest first principle. So first centroid is initialized somehow, and then we apply farther first max-min principle in 2 variants, using Euclidean distance and using aggregational dissimilarity measure. Also to these 6 algorithms. And we choose that the first centroid will be selected as the point closest to the global mean. It's our choice. It can be also other aggregation function used. So this is the calculation of selecting second and each other centroid. Thank you. This is modification 2a, where we use Euclidean distance, but in modification 2b, we compare it with modification that Euclidean distance is replaced by aggregation dissimilarity measure. All other steps follow modification 2a. Now we have here some testings. It's a methodology of tests. I will not read it all, but there were some data sets, some samples, and we run 100 random runs and evaluate them by this. These are external metrics, and these are internal metrics, saying about something about compactness and how are they correct, these models. And for modifications, we use this dissimilarity function, this order reversing map, and 12 different aggregation functions, 10 overlap functions, and arithmetic and harmonic mean. Also, we ran 100 random runs, but identical initializations as baseline, and we compared it by Wilcoxon signed Ryan test. In modification 2, there was only 1 run for all modification because it's non-random, and the comparison was we compared to baseline mean counts, and 2A versus 2B modifications. And here are sampling results. This is baseline results. I will speak very shortly about them because more you can see in the accompanying papers, which will be published maybe later. The winner is Siemens in the most cases, and Siemens plus plus. Sometimes these hybrid very bad results came in this dataset. So there were maybe overlaps between classes. And here are some results of modification 1. Especially it was more successful in external external metrics, but not in general through all used modifications, all used aggregation functions. Some particular improvements were observed in such some subsamples or in some algorithms and in some aggregation dissimilarity measures. And for modification 2, there were only improvements in internal metrics. But the winner of baseline was not overwhelmed. So it has limits in this modification have limits in these data sets, I think. It was not more effective in general, but as baseline, but can improve clustering quality in specific algorithm dataset, these modifications. And the main contribution is increased modeling flexibility beyond standard distances. Our future work, what will we do? It's deeper analysis of the relationship between data characteristics and aggregation-based dissimilarity effectiveness. And we can use alternative aggregation functions in assignment initialization, but also in centroid updates, other clustering algorithms, and so on. What is interesting that if we run in one subsample the Siemens, and we visualize in two-dimensional space, we get this interesting picture. Do you see something there? No, just kidding. But if you think that this picture is created by AI, you are wrong. It's really the result of fuzzy Siemens, but input data were generated by AI. So here are some referencing. Thank you for your attention.
Thank you for your talk. We have a very short time for maybe one question.
I have a question concerning slide number 13, if you can show it, because what you have is something like dual of the aggregation operator A, because you apply one negation before, one negation after, not necessarily the same. I expect that this composition is another aggregation operator, which could simplify this, so that I assume that all what you do with the inputs delta is another aggregation operator, which could be used directly.
Oh, thank you for the remark. I think you are right. But you say two aggregations. Here's one aggregation is
1 and 2 is another aggregation operator, which is also an aggregation operator, I suppose.
Yes.
Thank you. So now it's time for the second presenter, Inaki Presbyteriou. I hope I pronounced correctly.
Well, I present myself. I'm Iñaki Pérez del Notario. I'm a PhD, an industrial PhD student. I'm doing my PhD at a private company and at the Public University of Navarre in Spain. My company is about laboral risk prevention. We also work with the State Federal Agency of Meteorology and the government of Navarre that founded my grant, my PhD. I'm going to start by talking about my motivation behind my work. Here we have some families enjoying their time in the park. Suddenly it starts to rain, a very heavy rain. And the park is flooded and we don't know what happened with the people. And maybe if you, maybe you have heard about the event of the flood of Valencia in 2024, which caused more than 200 deaths and a lot of money. The very principal problem is that we didn't have any early warning, so most of the deaths maybe could have been prevented. I work with radar images. Radar images are as ground sensors that sense radio signals in a circular area, and the idea is that these waves are reflected by drops of rain and they return to the sensor. The time it takes to go and return and the intensity of the signal indicates the location and the intensity of the rain. Here we have every image in the radar Spain is taken every 10 minutes, which is very high resolution time in terms of meteorology. Here we have some forecasts for the episode of Valencia and another one for another episode of Spain, also of Spain, of Navarre, specifically in the municipality of Tafalla. These predictions have been done using a probabilistic diffusion model, a deep learning model that generates receives as an input a sequence of the last 1 hour of images and starts with a set of with a sequence of images with random Gaussian noise, and the model is iteratively subtracting noise from the image until we get a clear image. And this is the output and the forecast for the following hour. Well, the next step is to evaluate the forecasts. Here we have one forecast and the real value. You can see that the forecast is very far from the real value and the intensity that it predicts is far lower. So this is a very bad forecast. We have the other part, which will be an example of a reasonably good forecast. The prediction is not at the exact position, but very near. And the reflectivity is also very similar. What is the problem with this? With traditional evaluation metrics like mean squared error and mean absolute error, these metrics compare two images pixel by pixel. And what is the problem? Here they are on similar, on very close space, but it's not exact. So the error will be 1 + 1, 2, which is horrible. But as I said earlier, this is not a bad forecast. In meteorology, there's a state-of-the-art metric that is called fraction skill score, which takes into account spatial proximity. And I'm going to explain briefly how it works. It consists of 3 steps. First, instead of comparing the real image with a forecast, we choose an intensity precipitation value which we want to compare. If we want to evaluate the model with extreme scenarios, we will choose a very high value. Here we have some examples with two different intervals where we binarize the image, so it has values of zeros and ones. The second step is to pacify the image. We apply a diffumination filter that converts what it will be a 1-0 image to a more patchy ones where we diffuminate the borders. This is very useful because if we have the real value here and the forecast here, instead of having 1 + 1 error, we will have maybe 0.5 or 0.6, which is not zero, and is more accurate for this application. And the third step is to compare the falsified real images and the forecasts. Using this equation, which this equation returns a value within the range of 0 and 1. 1 will be a perfect region and 0 will be horrible. And as this function can be used with different intensity values, and the window sizes would indicate the degree of sharp if the function is more softer or more sudden. We have one problem with forecasts. Sometimes our forecasts are accurate, but in reality, most of the time not. And that's due to the chaos of the meteorology. The physics of chaos says that if we could have data with very high detail, we could make forecasts. But in reality, our sensors, image satellite images, they have intrinsic errors. And these errors may be low, but when you do forecasts at long ranges, it accumulates and can lead to vastly different outcomes. Well, as you might have heard about the butterfly effect, which means exactly that. Well, now we have to model the uncertainty of our models. One prediction, it's very unreliable, so we need more. As the butterfly effect says, small changes in initial conditions can lead to different outcomes, which can be seen here. That's one way of getting more samples. Another way is we have different trained models, maybe have been trained with different data of different hyperparameters, we get different results. So that also counts. We combine both, we could have here an ensemble of predictions. Well, now we have this. What do we do with this? Well, we can build a probabilistic images. Here, for every interval of intensity, we have a precipitation value and a probability that in the following hour, rainfall will surpass that value. With lower values, we have general more probability, but when we are increasing here, for example, the probabilities are very low. And another problem is that this way of measuring the probability, it's not, maybe it's a little bit difficult to understand to non-expert users. So we are going to simplify it more. With this probability mass, we build two scenarios of precipitation, one which we think is probable, and another which is an estimate. You can think of this as an interval of images. In this case, the probable scenario has been built for all the predictions, all the forecasts I showed earlier. In the probable scenario, we activate that intensity on image if at least that intensity appears on at least 60% of the images. In the extreme scenario, we want to go for extreme precipitations that may have that they are more difficult to predict and they appear less times, but are very dangerous. So in this case, we start with a 60% and we are progressively reducing the probability it needs a pixel to be activated when the intensity increases. Here we have an example where an extreme scenario can detect a very high, this yellow core of precipitation, which is real, but the probable scenario not. But this also can lead to false positives. So there's no perfect solution, and this is a reasonable way of doing this. There is a state-of-the-art aggregation function that is used in meteorology that is called probability match mean, which is very complicated. The idea is that it tries to generate a realistic forecast, but the way it works, it's a bit difficult. Yeah, and at first glance, it doesn't make much sense. I prepared here a diagram. Here we have, for example, 6 forecasts. And with this forecast, we calculate the mean of the forecasts. Then we convert both to vector format and sort them from higher intensity to lower. This is 6 times larger than this. And the next step is we pick the highest pixel of this and we change its value by the first one of here. When we go to the second, as here there are 6 more pixels, we pick the number 6. And iteratively until we end. And the last step is to reshape this vector into this original image, knowing that we have stored the original index positions. It's very strange function, but it was surprisingly good. Here I have some comparison with the FSS score, and this probability match mean gets nearly always the highest values. I didn't put it here, but we also tried using the mean, geometric mean, chocolate integrals, and other regression functions. Also, or probably both of these works give better results than our best individual model, which is also important. With an ensemble, we get more accuracy than with an individual model. The extreme scenario is a little bit lower, but it is thought to account to extreme scenarios, so it is normal. As future works of this project, we want to put these models into production to make forecasts in real time. And with that, we want to see how it works, how the users interact with them, and improve it even further. And also, this is interesting, this mean image that is calculated here can be also modified with another function. We tried some chocolate integrals and we got some interesting results, but I don't think at the moment they are that good, so I didn't put them here. And that's the end of my presentation. Thank you for your attention.
Thank you. Thank you for your presentation and interesting talk. We have time for some questions.
If you could go to the beginning of your lecture, please.
Yes.
I work with radars, and I know that they need to compensate for the fact that near objects have a much higher reflection, and apparently this is applied. Yes,
Yes.
that's it. Yes, but keep it, please.
Yes.
So apparently this is done, but in a strange way, because see, it seems that it rains on the radar all the time, so that there is some wrong input
Yes.
that shows that
Yes.
that the rain at the near places is stable and almost always present, which
Yes.
amounts for some strange mistake in this compensation, possibly.
Yes. This you make an interesting observation, because this is the episode of Valencia where we have very very high precipitations, and here we have one problem with the one limitation of the radar emitters with this attenuation. The radar signal are reflected by the rain, but in this case, it rains too much that the radar signal reflected here in the proximity, but it doesn't reach much far.
Okay, yeah, this is a persuading explanation, and then I recommend you to contact people who are working with ultrasound images, because they have this problem all the time and possibly can offer some better solutions compensating for that.
Also in Spain, where we have now antiquated radar technology, and they are now introducing a new type of radar that is called a dual polarization radar, with, in theory, works much better. I don't know if it will solve this problem. And another thing we can try is that we have a network of radars in all Spain. Here, in this case, the one in Valencia picks well the proximity of the base station, but the ones that are farther away, not. But if we pick the one here that will be in Catalonia, we maybe could pick this, and we make an image fusion, maybe we can compensate a little this problem.
Okay, since we are running out of time, maybe you can
Yes.
start later. Thank you. Yeah.
Can you show the email?
Ah, yes, yes. Okay. Yeah.
The next presenter is me. It is our joint work with Martina Danyakova from the Institute of Fuzzy Modeling, and I will start. This is joint work with Martina, and it is mainly done by Martina, the computation. It is part of the DigiBel project, which we are involved in it, and we are working for some time on it. The title is General Framework for Context-Aware Classification for Order Categories, a case study on BMI categories. And this is financed by research of Excellent on Digital Technologies and Wellbeing, which is co-financed by European Union, and it is supposed to bridge digital technologies to well-being. What is the motivation behind the study? We were studying the data for quite a long time. The data is not, it is not public, and I cannot disclose it, but what we face with it, that in many cases, people refer to BMI as a body mass index in a classical way, but it suffers from several points that I will mention here. In traditional BMI, which are crisp, it ignores the individual differences in the fitness and body composition. And it doesn't distinguish fat versus lean mass, which can misclassify athletes versus overweight people. And it might be two people with the same BMI as an athlete or sedentary can have very different cardiometabolic risks. So what is the purpose? It is here, and what we did, what is the objective? We wanted to develop the context-aware fuzzy partition for BMI categories to change the lines of the classes smoothly that cannot be crisp, and adopt the BMI boundaries using cardiorespiratory fitness. For short, we call it CRF, which is derived from VO2 max. Later, I will explain what is VO2 max because it is very important measurement in our data. And we employ Professor Novak's fuzzy context theory. He's not here. He would be happy. And implement it with the R package LFL, which is developed by Michal Burda. Yes, and what is the benefit? Is the smooth transition between adjacent categories, and it can yield to have more interpretable and personalized risk assessment, which is dedicated to the experts, not us. We just compute them. So what we did, the work is divided to two parts. One part is, as I mentioned, to use the Novak's framework, and the second part is to replace the crisp midpoint C with the context-dependent centers C prime to form VO2-driven fuzzy partitions. And how is the algorithm works? So what we need as a requirement in here, non-trivial data set that contains BMI values. Then we pre-process the data and check the parameters that are important to analysis to get adjuster, and then we normalize the adjuster. And then we compute the context-dependent centers C based on the adjuster, define the CTX3 based on the algorithm of Professor Novak. And with this, BMI can specific centers with the fixed boundaries. Then we construct the linguistic expression by the package LFL and define fuzzy BMI classes using the connectives by negation, conjunction, and disjunction, and summarize the result with recomputing the individual's membership, fuzzy cardinalities for each fuzzy class for the whole data set. So as I mentioned before, we derived the for BMI and based on VO2 max. But what is VO2 max? VO2 max is the maximum oxygen uptake during the intensive exercise, and the unit is milliliter by weight per minute. And it's measured by graded exercise test and indirect calorimetry. And in this case, the importance is that we can indicate the fitness and differentiate similar BMI profiles based on the VO2 max. But first, we need to normalize the index V, which is called index for fitness. We standardize the VO2 max for individuals with this formula. When V is 0, it is very low fitness, versus when V is 1, it seems that it has an excellent fitness. And the index can be refined for different topics like age or sex in the future work. We are planning to do it. And what is the interpretation? V is dimensionless. So it can be comparable with measures and the BMI can be shifted across the population. BMI boundaries can be shifted across the population. So here we have an example. If we shift the crisp midpoint C by the fitness measurement V as a C prime, alpha parameter is very important, and it is as a transformation parameter. If we set the baseline for 25 and alpha is 6, C prime 0 of 22 means that the person with the 0 fit should drop to 22, and with the complete fitness rise to 28. And the large V as a higher fitness raises the effective threshold, similar to the risk of the normal weight. But what is the BMI based on the World Health Organization categories? BMI is defined as a weight by unit kilogram divided by square of height by meter. And in the category of WHO, underweight is where the BMI is below 18.5. The normal is varied between 18.5 to 24.9. Overweight is between 25, 29.9, and obese is BMI above 30. This fixed threshold, as I mentioned before, it has different shortcomings. So we wanted to modify this category and see that whether it can be useful for us or not. Here, what we applied with fuzzy approach, replacing the crisp BMI with the fuzzy set. We have linguistic expressions. In our case, we use the preset interpretation of the specific linguistic expression based on the context, which is the bounded scales. And it is derived from the paper of Professor Novak. What is the linguistic expressions here? Small, medium, and big. For short, we call them as you see. And linguistic hedges, or we can call them also modifier. It is very roughly, for short, we call it VR. And logical connections here are negation, conjunction, and disjunction. And the context is left bound, middle point, and right bound. And as you see, we have the straight lines and dashed lines. Dashed lines are referring to the linguistic hedge, when we can smoothly transit the sharp fuzzy sets to the smooth fuzzy set. And the interpretation will be simpler in this case. So here, what we can do using the linguistic hedge and logical operations, we define these following classes. For overweight, for underweight, we use small x. For obese, we use big. Normal is negation of underweight, and negation very roughly of s. And overweight is the negation of normal, conjunction with underweight, and the negation of this. And as I mentioned before, with the WHO classes, the minimum and maximum for the BMI varies between 17.5 and 31. It is shown in these graphs. And then when we use the definition for defining this linguistic hedge, you can see that, for example, this normal graph as a overweight, it is more interpretable because it shows that when the normal is going down, the overweight is rising up. It is not like sharp change anymore. And this is the three different Cs that I defined before. The C25 here is the baseline, and the 24 or 26 are like shifting it to the right or left. When it is 24, as you see, the normal set is shrinking, and when it is 26, the normal weight, for example, or class is extending. And it can reflect the contextual threshold better. These are the distributions that we have from the data from the GBET. We had 1,314 number of participants, and BMI and VO2 max distribution for the classification are shown in the graph A, B, and the graph C shows the standard BMI classes without any classification. Then we needed to know that what is the feature importance for BMI classification. We did random forest algorithm to find the feature importance. I think in the beginning we had more than 20, but we had to filter them out to find the most important features. And they are lined by weight, VO2 max, which is the key fitness, and separates the similarity BMI by conditioning. Then it is the age, height, physical activities, and which can reflect the metabolic and lifestyle effect. And as we discovered, VO2 max is the most influential non-defining parameter, and it is the principal input for individuals' level BMI modification. Here, as I mentioned, the parameter alpha, which is the parameter for transformation. When we have the alpha for 4, we have the minimal shift, and you see the different bars for underweight, normal, overweight, and obese. For alpha 6, it is moderate shift, and when alpha is 10, it is the strong shift. And changing fuzzy set cardinalities across the categories by increasing the alpha. Basically, I can give the conclusion. What we did, we used some context-aware falsification, personalizes the BMI classification by using the fitness, and what we did, smooth transition between the categories, reduce the misclassification, and better reflect in real work risk. And we approach to some lightweight and interpretable for screening the population and clinical decision support. And what can be done in future? We can use nonlinear VO2 max transformation, or as I mentioned before, adjust the threshold for age and sex, and extend the multi-indicator health assessment, for example, for body fat percentage or waist circumference. These are the references that we use. The package R, which is, I think, publicly available, right? And the paper of Professor Novak. And here is the QR code for the repository, which is available in R. And partially the part that is for random forest is in Python. And that's all from my side. Thank you for listening. Question? I'm checking myself, and I think everything was clear, but but if you have any question. Okay, if not, thank you for your attention. So we have the last speaker, Remo Kali. He will introduce the work. This floor is yours.
Thank you. That's not mine. Yes, that is mine. That looks like mine. So thank you for appearing to my talk. And we're going to talk about responsible time series forecasting for this talk. So first, I need to give a little bit of an introduction of whom this is designed to help. This is in the field of electricity demand forecasting. So not only demand, but physical load in general. Because we have energy traders and dispatchers. They have 20 years of experience, more or less, and they work in very high responsibility and high risk applications. And the energy trader has a little bit of a problem. You see, in the last few years, his knowledge or his experience is a little bit tackled, or he has some issues because we have lots of integration of renewable energy sources, which act very stochastic. And so what happens is that his experience sometimes might be a little bit misleading because the patterns, they shift. And so the models they have and deploy, they deteriorate every year, and they need some kind of assistance in that, or need to understand what is happening. One of the reasons you can think of is heat pumps, or overall heating that is more done by electricity than by gas. We have electric vehicles that have an influence on the energy consumption, and also solar power production, of course, that influences this behavior. So his problem is his decisions are very costly. So when he makes wrong decisions, he has to, for the next day, order the energy mix for the next day based on his forecast and assumptions. So when he looks at the load curve, he needs to identify how much energy does he have to order from perhaps atomic power plant, how much does he can rely on solar power, and how much insurance does he need, or how much contingency budget does he need to reserve. His decisions affect a lot of people, right? So especially in Switzerland, where you cannot really change your energy provider, you are set with the one you have. And when he makes costly decisions, the costs go directly to the citizens themselves, right? And so what he does is he has a lot of models, but in the end, he needs to decide on what do I need to purchase the next day. And he has a little bit of often these models have the illusion of accuracy. So accuracy is, they can range from a few percent to 20%, depending on the region or depending on the temporal window you have. And as said earlier, it's increasing every year, basically, because we introduce more and more renewables into the grid. So what is kind of like my motivation in this? I worked for the past few years with these energy dispatchers together, and try to help them understand what is the impact of renewable energy sources for their grid, and how to introduce them better into the power mix. Then further, we have investigated in what kind of methods could we employ to better integrate this uncertainty. And we have seen that there are currently few to fuzzy data and TSK applications. So we thought that would be perhaps a good idea to explore a little bit the possibilities we have of this. And we want to go a little bit away from the pure point prediction accuracy paradigm because it yields diminishing returns based on the complexity that we invest. So when you have different models, then the question is, which model do you trust, or which do you trust more? Because each model that we have, each time series model, there are many different kinds and schools that you can follow, has different strengths and weaknesses given on the specific context. So you can think of it like some models are strongly dependent on the weather forecast, right? When you have strong temperature coupling, like in winter, you need to heat. In summer, you might use your AC. So this is strongly correlated to the temperatures you use. And when you have unreliable features such as the weather forecast, then a strong reliance or a model that relies strongly on features might be misleading in these times. Other things are perhaps anomalies or rare events, such as holidays that are in the midst of a work week that might overfit or that might be too sensitive for these kinds of scenarios. And the other thought we have is then based on the limited data that we have or the context that we can learn on, that certain occurrences such as anomalies, they appear or they are less frequent than, let's say, weather uncertainty regions, right? So you cannot really robust test how a model responds to anomalies. So the idea was to give these kind of anomalies less weight or less be more considerate about these features. And so for the testing setup that we choose, which have all open source data, by the way, is from comes from the ENSO-E platform. You can, it's a very nice website. So if you want to see something with energy data, to check it out. There is also your country listed with what is the energy mix and what is the production and consumption. So it's a good way to get some data. But it essentially combines the transmission system operator, the TSO, and the distribution system operator, the DSO. So that is one level below, right? So you can think of it in scales. TSO is more on a national level, and DSO is more on a municipality level, right? And of course, exogenous data such as temperature forecasts, which are provided by OpenMeteo, but essentially are refitted or transmitted ECMWF data. So to test these kind of uncertainties, we produced out-of-sample predictions or residuals from the year 2024 and 2025. And it defined different contexts that we wanted to encode, right? So first we had volatility that we thought would have, or we think has an impact on the model's residuals, right? So certain models are better suited during high volatility regions. And we measured this by the realized volatility during a whole day, measured and averaged over 3 days. So we have kind of regions where we can say we are in a high volatility region or not. The same goes for weather. Here we can really compare the different weather forecasts, how they developed at a given time, right? So I know what the weather forecast is for tomorrow. So when I compare it to yesterday's weather forecast, I can see if there is a large difference or not, right? And typically, weather forecasts, they have regions where they are less reliable than other regions, such as in I think in September or in April, they are like these shoulder regions where they tend to be a little bit more unreliable. We have rare events, so it's a little bit a paradox. Expected outliers, they're not really expected outliers, but we have special holidays like festivals that don't really make sense, that we can not really learn from these, but it's just an uncertainty that we introduce at these days. We have non-linearity measures. This one is a little bit different or difficult to understand, so I brought an example with. This would be a typical load curve from January, and what we see or what we call these kind of hills is that we have this pre-mid-day ramp up, and then usually we have like a valley that is introduced by people not working, first of all, and of course the solar power impact that you have because it displaces a lot of the necessary energy you have. And so there are also certain models that can fit to these kind of hills very well, and some very badly. And so we need to kind of like hatch a little bit around and see what works best. And so when we look at different models and different contexts, we can a little bit characterize the different regions. So on the left side, I know it's a little bit small, so I read it to you. We have, for example, the context for the 9th of September 2025, or the 4th of September. We have a medium volatility profile, right? So the membership for volatility would be set to medium. We have, for example, the weather is quite volatile at this time, so it's a rather unreliable feature. And so this is just the profile that we expect for tomorrow. On the right side, we have a model. In this case, it's a Sarimax model. And we observe that this model is not, has not very distinct preferences on whether it is good or bad on volatility. It's in the middle, so in ensemble speaking. But what we see, for example, is that it is very bad when we have anomalies or when we have something in the midst of the week that disturbs the pattern, right? And so when we have these two kind of characteristics, we can combine them with some rarity as well. So we can say how prevalent or how often is this kind of feature present, or this membership function, how often does it appear in the data? And so we can tell whether it's a reliable feature or not. And when we combine this with the membership function, we get very interesting kind of fields of uncertainty that we are not very confident on making, but we have like in the middle where we see, okay, it's probably a good feature because it's in this kind of setting and context, it appears quite a lot. Now, based on this, we can actually learn an inference system, right? We can set the function that we want to optimize. In that case, we want to minimize the MAE with a scaling factor, and we have our rule sets that we can define. In this case, we have 9 models, and we have 14 different contexts as a consequent of the function that we have here. And together we can then make an inference based on this function that we defined. We can reduce it and learn what is the best allocation of different weights. And we can use these weights and transform it with softmax and get a final prediction that is based on a point prediction itself. And when we look at the results or how they develop, here's also the models that we used, by the way, you see that it slightly outperforms the simple averaging method that we have here. So this is the uniform method, and this is the ensemble that we have. So there's slight improvement to this inference currently, but what we wanted to see is there actually a change in allocation of the way it's happening? Which it does, and this is very good. It's what we wanted to see and expect, right? We have overall we have one model that is very strong. So this is the light GBM model that is capable of fitting very well and very complex patterns, and we have sometimes increase in statistical models like the Holt-Winters model, which is essentially triple exponential smoothing that does not rely on any features at all. It's just a function of the autocorrelation itself. And here we see sometimes it works quite good. We have increases in weights here, decreases in weights here. Here we have a disparity between the ML forecast or the light GBM and the winter holds, and they kind of try to alleviate each other's strength and weakness profile. And at the bottom, you see we have a purely statistical model that is the MSTL model. It performs quite poorly because it is basically not really capable of fitting these dark hills that we mentioned earlier, because it's essentially just a decomposition of time series with multiple seasonalities. And it's also a very expensive model, so inclusion should be justified at this point. So let's talk a little bit of what worked well. So we think that the model strength and weakness profile, they are very good to understand as a user. Because what we see with these energy traders is when we give them forecasts or predictions, to them it's very difficult to understand why is a model performing well and why is it performing bad. Because usually these people are not statisticians. And of course, we can make use of explainable AI techniques like Shapley values or Lime, but just because we can explain it, I mean, we can explain the coefficients of an Arimax model or statistical models, or we can explain F-scores from machine learning model. But the thing is, these people, for them, it's sometimes difficult to understand what is a feature importance and how well does it work and how does it influence my uncertainty that we have. And so this kind of strength and weakness profile, to them, it's easy to understand, and they have a good idea of what to expect the following day in terms of residuals and contingency management. Then the fuzzy proxies that we have, or these kind of contexts that we defined, they help to understand the prediction difficulty, as mentioned. So when we have high volatility, thank you. When we have high volatility, then they know, okay, we kind of expect a lower accuracy at this time. And the third thing we think the TSK learning showed, even though it's just slight improvements, it showed that it was capable of assigning different weights to it. And so what can we improve? And I get to future research after this. We have found that different data requires different proxies or different context windows. So as an example, the different temperature coupling, right? When you look at it on a municipality level or on a household level, energy or temperature coupling is very strong, right? So when it's cold, you turn on the heat. But on a national level, these kind of effects are very strongly aggregated. And so you have a fewer and less sensitive temperature coupling than otherwise. The rarity function that we have, they kind of like draw from the same distribution, and therefore there is not. It's difficult to justify this that we have this kind of field of uncertainty, because it essentially it kind of is in the same field as the different membership functions with its prevalence. So what we think it guards, or we see that it guards against extreme events or extreme features, we need to justify this kind of complexity that we have in the inference system. Maybe a simple type 1 Mamdani system would probably suffice, but that is subject to testing. And what I also wanted to say is, you have seen that one model really dominates the whole weight. This is a common problem in assembling when you have large diversity. And this has also some implications that I will go back to. Then there is many tunable parameters. So we have much parameters that we need to control of and see how they influence the results. And the softmax is removing a lot of type 2 behavior that we initially wanted to preserve. So where do we go from now? We are trying out different specialized context-based models that are really good at predicting certain contexts or certain times. We can do this by temporal bagging or curating our input data to a level that we really can control what is the learning that is happening there. So you can think of when you work with images, it's like data augmentation, right? They have a high risk, high reward profile, but then we can guard against these risks with the inference itself. We want to try out different functions for rarity so that we have a more diversity in the different assumptions that we have, and to better propagate this kind of field of uncertainty towards the prediction itself, and maybe even embed it as an interval of uncertainty. And again, here we must consider the complexity trade-off for reward and complexity that we have. And the final thing that we want to test is the linguistic summarization, and I think it's best explained here in my final slide. We want to have a user study to how we can explain what is the context ahead for tomorrow. What is the profile that we assign it to? So we say, for example, tomorrow's weather for uncertain. Therefore, a Holt Winters model performs better during this context. Therefore, the consequence would be to assign more weight towards this model that performs better. So, and we hope with this, the energy traders are better at understanding what kind of decision they make, and to have more responsibility in their decisions. Yeah, so thank you very much. And yeah, I think that's it.
Thank you. Is there any question?
I have a simple question and one comment. The question is, the forecast is done for the next time moment or for some longer future?
The forecast is always made for 24 hours in advance. So think of it like we have today at 7 o'clock, we need to make the decision for the following day. Yeah. Then we need a complete window of 24 hours that we order energy for this mix.
It means that measurements are done every hour, yes?
Yes.
Yep. Yes. And my comment is I have serious doubts about sensibility of using type 2 fuzzy sets, because the fuzzy set, the membership degree is a degree of truth of having a property. And one concrete value of membership degree has not a real sense. The sense has tendency and ordering. And in type 2, this is only pretending that to be type 2, because always, and it was also in one of your years here before, simply you replace this, how to call it, simply these areas.
You are correct.
I forgot the name you call it.
Or the rarity function.
No. This. Okay, it doesn't matter. Simply you replace it by one concrete value, and you are back in fuzzy sets. So forget about fuzzy sets too.
That's a very good remark. And we were actually also looking at that because we could just also adapt the membership function to be more in line with the lower bound of this field of uncertainty, and we probably would have the same results. Yeah,
for sure.
Yeah, thank you very much.
Thank you. Quick question regarding uncertainty. Could we reduce it by just promoting nuclear energy and getting rid of green craziness?
Say again, sorry.
Could we just reduce all the uncertainty of all this problem just by promoting nuclear energy and getting rid of green craziness?
Well, I think nuclear energy is a little bit of postponing the problem, right? Because it's not really solving all the problems. Nuclear energy has very, very beneficial properties, right? It's a very strong baseline. And in the end, you're also just turning a steam engine in this nuclear energy. And so while it's not really a problem in terms of pollution itself, when you consider the finite resources you still need, it has a very distinct profile. The issue is that it's very difficult to order more nuclear energy on an intraday level, right? While when you have this very set level of energy that you order, you cannot just spin up another nuclear energy facility for half an hour and then spin it down again. So this is kind of like the problem. And you have, when I can show you this, you could, or what you do is like you order a strong baseline here from nuclear energy because it's a very set level. And then you see how you will solve this kind of ramp curves, which needs to be with more flexible types of energies. Was a good question. Thank you. Yes. Yep. Exactly.
Thank you. Can I have one question?
Yes.
As far as I understood, you are using context variable per rule, right?
Yes. Yeah.
Aren't you worried that your model performance might degrade? Like you have high temperature and high volatility in this case, how do you interpret it?
Then you have combined context to mean. When you have
Yes,
high
yeah.
volatility and high weather
Yeah.
uncertainty, then you would need to find something that satisfies both rules, but in a more conservative way. When we see in general large deviations, then we generally tend to go back to statistical models because they are more stable during these times. Because exogenous features, they can really derail your predictions. And so we need to be careful with those.
Thank you. Thank you. If there is no more question, I'm closing the session and enjoy your lunch. Thank you.
Thank you very much. Oh, yes. I thought I could keep it.